And we're back. So you remember our buddy lambda? Lambda was the unit interval 0, 1. Take away the union of all those A's. The left-hand side folks are everybody who didn't go away. And the claim is lambda is a Cantor set. So what is a Cantor set? What I made a point of saying the Cantor set before. A Cantor set is a set that satisfies those three properties that we observed about the original classic Cantor set. That is that it's closed, it's totally disconnected meaning no intervals, and 3 means is perfect, where perfect in this topological context means every point is a limit point of some other points in the set. And the Cantor set, the classic middle third set, did that, and our lambda construction here looked similar, but we weren't doing that geometrically. We were doing that as a collection of points that satisfied some constraint on the dynamics of this dynamical system that we're looking at. And so it's not exactly thirds, but the construction is similar enough that it's pretty believable. So here we go. The proof in the text is on pages 37 and 38. It's one of the places where they're pretty dense. So, and what they claim right away is that we need a little more hypothesis to facilitate some calculation. And that, remember we said in our description earlier, for mu bigger than 4, that's exactly what it takes for the function to bump out of the box a little bit. Because mu equals 4 is where you bump the top, so mu just a little bit bigger than 4 is enough. But in able to make the calculations work, what we need for a relatively easy proof is you need mu big enough so that f sub mu prime at a bunch of points x is going to be greater than 1 for all x in I0 union I1. Remember those? I0 union I1. I0 was the points on the left that didn't leave immediately. That's A0 in the middle, and I1 were the ones over there. So all of lambda. So remember that lambda is contained in I0 union I1, the big set lambda. So if we're having some constraint that allows us to say blah, 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 blah about all x's in there, then in fact what it's also telling us is blah, 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 blah about all x's in our set lambda. But it's going to be useful to be able to say it that way. So if we have this derivative big enough, we're going to be able to use some tools that we have in our toolbox. It's going to be handy. And so the question is, can we make mu big enough that will make this derivative constraint true? And they tell us that we can, but let me just investigate the picture a little bit more. If it's a little bit outside, but not too much outside, but not trivially outside, see, if you have the slope at this crossing point here, I mean, after all, that's the edges. Those are the edges of the definition of I0 and I1. If we have the slope exactly right there is 1, just at the magic point where it crosses, then back here the slopes are all bigger than 1. Right? And here, if we had the slope, well, of course, it's symmetric, right? If the slope there is 1, the slope there is going to be minus 1, then the slope everywhere over here is going to be more negative than negative 1. So the absolute value is bigger than 1. So all we need to be able to make this constraint hold true, that the derivative is big enough everywhere in here, is that the derivative is big enough at those two exit points. And since they're just symmetric, then that means we can really look at that guy and try to do some calculation. And figure out what's it going to take for the mu for the slope on its way out the door to be bigger than 1. Well, in fact, if that's the slope there is equal to 1, then it means everywhere in here the slope is going to be bigger than 1. So what we really want to find is that this is the edge. So, as usual in lots of places in algebra and analysis, to find out where something is bigger than 1, you find out where it's equal to 1, and then that's the edge of what's enough to make that take place. All right. So here we go. The text says that I forget what they say, it's easy to show, or the reader may check, or a small child could show, or one of those typical kind of phrases where they say it in one line. And I just want to go through it as an illustration of what's going on. So let me see if I can reconstruct these computations. So from that picture we had a minute ago, let's come on down here. We want two things to happen for that point right there, and that is we want it to be a point where it actually hits the edge of the box, which means f of x, if that's x, we're trying to find the appropriate x, f of x equals 1, right, for this particular function. And the other thing we want is the derivative of the function at that point to also be 1, and then we can say everybody left of there satisfies what we wanted to. So to simplify calculations, we're going to just write f instead of f sub mu for a few minutes, just because we're writing f of whatever. So what are those two things we need? We need f of x, which is mu x minus mu x squared. If we want the x that we plug in so that when we take f of x we're exactly equal to 1. Well, then we set it equal to 1. How hard could that be, right? And so that looks quadratic, so you take that over there, you get mu x squared minus mu x plus 1, and we got a formula for stuff like that, right? You could solve for x as a function of mu, so it's minus b plus or minus the square root of b squared minus 4ac all over 2a. So one of the constraints on the x is that. It's not pretty, but it's not hard. So the other constraint that we have, I'm going to try to fit down here, the other constraint is that we want the derivative, which of course is mu minus 2 mu x. We've done that a few times already. That we want the derivative when we plug in that particular x. We want the x that'll be that when we plug in that x, we get that derivative to also be 1. Well, if we could solve that for x, we have mu minus 1 equals 2 mu x. So if you divide, you get mu minus 1 over 2 mu equals x. Oops, there we go. So we have x equals this and x equals that, and so for x to satisfy both constraints, we ought to just be able to set those two mu expressions for x equal to each other and go crazy and solve it. So let's see. Let's see what we can do here. So if we put mu minus 1 over 2 mu, that's that x, we set it equal to this one, which is mu plus or minus a square root over 2 mu. Well, already the 2 mu's in the bottom are gone. That's pretty cool. We know mu is going to be bigger than 4 anyway, so it's not going to be 0, and we're not doing anything crazy here. So if we multiply by 2 mu, we get mu minus 1 equals mu plus or minus blah 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 mu squared minus 4 mu. So darn, even the mu, you cancel mu's now, right? So you got minus 1 is plus or minus, well I bet it's minus, mu squared minus 4 mu, right? So, well, if that was minus, then that one's got to be minus, but still, then we multiply by both sides, we get, you square both sides, right, to get rid of the square root. You get 1, and over here you get mu squared minus 4 mu. And you go, all right, maybe that means more quadratic, right? You drop that up there. I'll see what I can squeeze on here. So 0 equals mu squared minus 4 mu minus 1. Just from there, bringing the 1 over. So here we go. So again, this formula is coming in handy twice in one day. So mu is minus b plus or minus the square root of b squared minus 4ac all over 2. Which I think I can simplify. That's the square root of 20. And the square root of 20, as you can factor out the 4, turns into a 2. And then the 2 simplifies, and you can go 2 plus or minus the square root of 5. But since that's mu, cool. Well, since we know the mu is not going to be some negative guy, then you choose the positive answer. It's the one in the range of what we're considering. So mu is 2 plus the square root of 5. So since that's the value of mu that made us exactly right there, made the slope 1, then if we pick a mu bigger than that, then what's going to happen? If mu is bigger, then everybody's just a little bit taller, and it's still steeper, and then it comes around here, and it comes down like that. And so it's a little bit steeper than it was there. So the derivative is a little bit bigger. So it's pretty clear that if that was the edge that didn't give us what we needed, then we need to pick mu greater than 2 plus the square root of 5. And that is what's going to give us the constraint that the slope of this curve, everywhere in here, the derivative is bigger than 1. And correspondingly, because of the symmetry of the parabola, everybody here has the derivative is bigger than 1 in absolute value. There's the minus version on that side. Okay, so this whole page and a couple of quadratics, and this whole page is where the author says the reader can check. Yeah, right. Thank you very much. So now we can move forward with that assumption. So we assume that mu is greater than 2 plus the square root of 5. And what that's going to give us is that the size of the derivative is bigger than 1 for all x's in I0 union I1, which includes lambda, but then some other folks in case we need it, right? So, as you may recall from an earlier proof that we went through a week or two ago, the fact that we have an open inequality here, that it's not greater than or equal to, but it's greater than, if that's true for everybody in there, then that means that we can then, what we call bound it away from 1. There exists some number lambda greater than 1, so that the same thing is true, that we can at least get f prime of x greater than lambda, which is greater than 1, for all x in there, but we're going to need it to be true in lambda. Now there's that lambda, there's that lambda. I don't know why people do that, but I'm just trying to match the notation in the book. And that's because the big set lambda is a subset of there where we just made the claim true. If it's true for everybody in here and everybody in here, despite my bad artwork, oh there it is, yeah there's the other part, then lambda lives in there because that's the A0, so none of lambda lives in there. So we can get the derivative bigger than lambda. And you remember when we had it bounded away from 1 before, it was because when we wanted to repeat something repetitively and multiply by itself, we didn't want different lambdas approaching 1, because then you could only have something greater than or equal to as you took that iteratively. So what we've got is, for folks in lambda, in the big set lambda, the derivative is bigger than 1. Well, what we claim is that then we can look at the chain rule and draw a conclusion about the derivative of the iterates of f. So you take the nth iterate of x and take the derivative of that. The derivative of a composition is when you do the chain rule, and we talked about this before. And what happens is you can prove that that then is greater than lambda to the n, where that's the n and that's the same n for all x again in lambda. And that goes like this. To be able to analyze the derivative of the nth iterate, then the derivative of an nth iterate is, well, that's f prime with the rest of them still inside, times then the derivative of the insides. And the derivative of an iterate of somebody is the derivative, and then you leave the rest of them alone, times the derivative of the inside. Remember, that's the chain rule, is always the derivative of the outside guy with everybody inside left alone times the derivative of the next guy. And so that's f prime, I'm doing this one now, where you left behind n minus 3, times the derivative of what's inside there, and sooner or later we got to write dot 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 here, right? And so that in the next, at some stage you're going to have f prime, and there's only going to be maybe 2 of them left in there. And then it's f prime with only 1 of them left, and then finally it's the derivative of that guy, and the derivative of that guy, I know, it's f prime. Duh, finally I can write just f prime. And so this is a place where we discussed the chain rule before. It was really pretty handy. So the thing to observe here is because x is in lambda, then x and f of x and f of that and f of that and f of that, those are the folks that stay inside forever. So x is in lambda, and f of x is in lambda, and f of x is in lambda, and f a few times is in lambda, and f a few more times is in lambda, and f a bunch of times of x is still in lambda. All those little folks that I just drew little red guys around are all in lambda. So that means each one of these things with a circle around it works in there, because that's f prime of somebody if somebody's in lambda. And all those guys are in lambda, so that is then an absolute value greater than lambda. And that in absolute value is greater than little lambda. And that in absolute value is greater than little lambda. Because then what you do is you say absolute value of that is absolute value of that one, and absolute value of that one, and absolute value of that one, and absolute value of that one, all the way to the end, right? And so that's bigger than lambda, that's bigger than lambda, that's bigger than lambda, that's bigger than lambda. So this thing with the absolute value here ends up being greater than lambda, and there's n of them. And that's what we claimed you could use the chain rule to do. Okay, well, what is that good for? What we want to do is we claim that lambda contains no intervals. Containing no intervals means totally disconnected, which is our property number 2. Gee, Doug, what happened to property number 1? Property number 1 to be a Cantor set was that it's closed, but you remember all those A's, I actually may have said this before, all the A's were open sets, because you had to leave the endpoints behind because the endpoints always end up going to 0, so you need them. So you're taking out a union of a bunch of open sets, and so it's closed. So we already sort of had number 1 is done, it's closed. And so this is dealing with property number 2 of those 2 properties that we're trying to show. That lambda contains no intervals. So how are we going to do that? We're going to assume not and look for a contradiction. That is, we're going to assume that there is one. There is a closed interval in the set lambda. And if there's a closed interval in there, that means we could find these 2 points x and y that are in lambda. And they're actually different points with all of the closed interval x and y also contained in lambda. So let me see, we've negotiated on the previous page up there something about derivatives being some inequality with derivatives, and now we're talking about intervals. I feel the mean value theorem trying to appear here is what I bet's going on. Because you got derivatives and intervals and things, right? So what we've got from up above is that for any number in this interval x and y, where x and y are these particular 2 points now in this assumption. Here's the assumption, right? That we've got a couple of points where everybody in between them all stay in the set. But we know from that previous page of conversation that for anybody in there, any alpha that's in there is also in lambda, because we just said the whole interval is in lambda. So that means all that stuff that we said before is that the derivative of the nth iterate applied to that alpha is going to be greater than a lambda to the n for any alpha that's in between those two, because we're claiming that the whole set is in lambda. So now what are we going to do? We want to make somebody big. Since lambda is greater than 1, and we're using the same lambda. See, that's what's important, the same lambda over and over again. That's why it was important to bound that original derivative away from 1 and then reuse that guy to get this nth power thing going here. Since the lambda is bigger than 1, excuse me for a minute.